Hello, fellow students, and welcome to this lecture. Today we are going to talk about Eulerian and Hamiltonian paths, so stick around and enjoy yourselves. And this is the problem that we have for today. It says like this. You have 10 steel pieces that must be staked in a specific way, where they stick together using a small crane. The problem is that the pieces have two different sides with different rugosities. And for two pieces to stick, the necessary and sufficient condition is that the contact surfaces have the same kind of rugosity. Considering the following configuration of rugosities, and you have this table here, can the pieces be staked? If the answer is affirmative, please specify the staking order. Well, if we look into the table of rugosities and pieces, we can see how we have 6 different rugosities from A to F and 10 different pieces. Each of the pieces will be linked to 2 rugosities, one on each side. So for instance, to stake together 4 and 5, I need to do it on the rugosity on the side that has the rugosity A, right? Because this will allow them to stick together. And the answer, the question is if the pieces can be staked, right? And then if the answer is affirmative, please specify the order. So yeah, they are asking just in which order can we put these pieces one on top of the other, taking into account that each face has this rugosity, right, as it is explained here. Well, the first thing that we must review is the concepts of paths, right? We have the Eulerian path, which is a simple path in a graph that visits every edge of the graph. And remember that a simple path is the one that only passes once by each path, right? So it will visit only passes one by each edge, right? So it will visit every edge of the graph passing only once. And then we have the Hamiltonian path or Hamilton path, which is an elemental path that visits every node of the graph. So if we remember from the previous lessons, that elemental path is the one that passes only once for each node, right? So this one will visit every node and passing only once for each node. Okay, so how can we model this problem like a graph? Well, we have two options, right? We can make a graph where the rugosities are the edges and the pieces are the vertices, right? Or we can do it the other way around. Let's start by this one and let's see what happens. Right, so to model problem, we will try to build graph where the rugosities are the edges and the pieces are the vertices. To find order, we must pass once for each piece, which in this case is each vertex, so we must find the Hamiltonian path. Okay, so how is a graph where the pieces are the vertices, right? Let's do it with the first row of the table. So if we take the pieces 4, 5, 6, and 7, all of them are linked by the rugosity A, right? All of them are linked by the rugosity A, but also 4 and 6, and also 5 and 7. Well, if we model the problem like this, we could have configurations that are invalid. So for instance, this path 4, 5, 6, 7 is not allowed because the piece number 5 only has one side with the rugosity A, right? The other rugosity is F. So this path wouldn't be valid. So let's write it down here. If we model the problem like this, we can have configurations are not valid. For instance, the Hamiltonian path for A1, 5, yeah, this should be different relation, right? Can't have exactly the same name. Uh, 5, A2, 6, A3, 7. Allows to stick the piece number 5 between 4 and 6 when it only shares with them the rugosity A by one of its sides. So if we stake it with 4, we cannot do it then with 6. So we are going to try the other approach, okay? To find a valid configuration, we are going to build a graph where the rugosities are the vertices and the pieces are the edges. Okay, so let's see how this graph is, right? If the rugosities are the vertices, I can start drawing the rugosities. And I will start by A. And I have E. We have D. We have C. We have F. And we have B. Okay, this will be the vertices. And now we can put the edges, which will be the pieces. So for instance, we have the piece 4 between the rugosity A and the rugosity C, right? Because the piece 4 is in the first row, and then it is in the third row of the table. So it will join A and C. So we put here the piece 4. We have 5 between A and F. Between A and F. We have 6 between A and D. And this is 6. And we have 7 between A and E. So this is 7. And we pass to the next row, where we have the piece 1 between the rugosities B and C. Then we have the piece 2, also between the rugosities B and C. And we have 3 between C and F. We have done 4 already, and we have 9 between C and D. We have done 6 already. We have 8 between D and E. And we have done 9. We have 10 between D and F. And that's all, right? We have the 10 edges already. The other ones are repeated. So now, once that we have the graph, we need to think what kind of path we need to define, right? If we want to pass once by each piece, which are the edges, we must define an Eulerian path, right? So let's let's write it down here. As the pieces are the edges, to find the order, we must pass once by each piece. So by each edge. That means that we need to find an Eulerian path. Okay, now to find the Eulerian path, we need to follow an algorithm, right? We need to follow an algorithm. I think that I'm going to do it in the next page, because here I don't have, I don't have much space, right? So let me remove this. We need to find an Eulerian path, right? So now we are going to start with the algorithm. Right, and the first step is to calculate the degree of the nodes. Okay, so let's calculate the degree. The degree is just the number of incident edges in one node, right? So, for instance, we have 2 edges here, we have 4 edges here, we have 5 edges here, we have 2 edges here, we have 3 edges here, and we have 4 edges here. Okay, so now what the theory says is that if all the degrees of the edges are even, there is a closed Eulerian path. But if there are 2 odd degrees, like is the case here, right? We have 2 odd degrees. That means that there could be an open Eulerian path, right? So let's write it down here. We have exactly 2 vertices with odd degree. There is an Eulerian open path in the graph. Okay, so now In this case, we need to add an extra edge between the odd vertices, right? We need to add a fictitious edge between the vertices with the odd degrees. And we will call this edge X. So we just need to add a new edge, right, between C and F. Okay. Now, once that we have added the new edge, we calculate a simple starting path. Right, we take a simple closed path in the graph. So for instance, if I start by B, I can go to C through 1, then I can go through 4 to A, then I can go through 7 to E, I can go through 8 to D, through 10 to F, through, let's use X, through X to C, and then again to B. So this is the simple starting path, right? Let's write it here. Once that we have the first path, we remove from the graph the edges that are part of this path. Right, so at the end, if we remove all these edges, right, we have the same nodes, which are E, A, C, B, F, and D, and we have the remaining edges, right, which are the inside ones. These ones, right, that we didn't use. And 3. Now, for each connected component, for each connected component, and if you want to review, if you don't remember and you want to review what is a connected component, check the last videos where we explain this. With edges we repeat this process, right? So we calculate a path in the subgraph, right? So for instance, in this case, we don't have many options, right? But we can start by A. With 6, we go to D. With 9, we go to C. With 3, we go to F. And with 5, I come back to A. Right, so this is the path. Now what we need to do is to insert this, well, after you are done, for each connected component, you will have a path that you will need to insert in the main path. And how do you insert this path here? Well, you do it taking into account that the starting point and the end point of this path are in the original one, right? It will be here. So we just need to substitute the node A here for the full path that comes from A. So we insert the path in the graph in the simple starting path. We start, we go from B to 1 to C to 4, and here, right, in A, we take this, right? We take this path and we paste it here. And then we continue with the rest of the main path, right? Finally, we have something like this. And this is the path that we inserted. Now, the last step is to remove the fictitious edge. We need to remove the edge X. And now to remove this edge that is here, what we do is, okay, let me clean up a bit here. If you remember at the beginning, we said that we would have a closed, open Eulerian path, right? And until now, we have a closed path because it ends and starts with B. So to remove X, we need to make it open. And to do that, this will be the last node of the path. And this will be the first node of the path, right? So at the end, we have something like this. And we can remove B because it's the same node, right? Here at the beginning and at the end, it's the same node because it's a closed path. So we remove X and we make it open, right? This will be the first part, and this will be the second part with the final node of the map, of the graph. Okay, so finally, we have an open Eulerian path, right? If you check it, or by C, 2B, 1C, 4A, 6D, 9C, 3F, 5A, 7E, 8D, and 10F, right? So it's an Eulerian open path. So we have already the staking order. Staking order is, we just need to take the pieces on this path, right? Which are 2, 1, 4, 6, 9, 3, 5, 7, 8, D, and this is the Eulerian open path. So if we go to the original table, you will be able to see how we can stake together all these pieces on this order, right? Because, for instance, 6 shares a rugosity with 4 and a different rugosity with 9. So that's all for today. I will stop sharing the screen now. And as I said, that's all for today. Thank you for joining me on this lecture. As always, if you have any question or you want to talk about any mistake that I made during the talk, don't hesitate to ask, don't hesitate to write in the comments, and I will have a look. So thank you for watching me, and goodbye.